Can be, I guess. Okay, so this section here deals with radicals. So if you look at the top, okay, you see it says free radical substitutions and additions. This section basically just deals with nothing more than chapter 10. So these are all questions that have something to do with chapter 10. And I want to ask you guys, I know we're online, I know it's not always fun to answer questions online, but I want to ask you guys question number 1, okay? This is something we talked about last class. Which one of these radicals is the least stable? Can anybody just point to one and be like, you are unstable? This radical is awful. Yeah, thanks, Jenny. Absolutely. Yes. Okay, so Jenny nailed that one pretty quick, okay? Right? Like I went over with you last class, if you see a vinylic radical, anytime you have a double bond and then you have a radical on it, that is a huge no-no in organic chemistry. It's the same thing as if you were to have a double bond, whether it's just a plain old double bond like we see here, or in an aromatic ring. And if you see a carbocation, again, that's a big no-no. A vinylic radical is very, very unstable. And if you want to go back to some of the rationale why, I mean, the rationale that they gave us in Klein was all based on bond association energies, okay? So what it means is that if you look at this molecule, right, this bond, okay, well, maybe not that one, but let's say this bond here, which is a vinylic hydrogen, that would be a very strong bond. It's very difficult to break that bond. So vinylic radicals, highly, highly, highly unstable. So we don't want to see any vinylic radicals. Okay, after that, I had question number 4. So let's go over to question number 4, which is down here. And this one deals with our anti-Markovnikov addition conditions, right? HBr and peroxides. And instead of writing peroxides, they could have written ROOR. That's totally fine. They just wrote peroxides. In this case, we have a symmetrical alkene, so there's no Markovnikov or anti-Markovnikov to speak of in this particular case, right? It's not a thing here, but we still know that the mechanism involves initiation, propagation, and termination, right? And without going through the whole thing, right? The initiation was the peroxide breaking apart to make a radical, then reacting with bromine or HBr rather to make a bromine radical. So could anybody tell me which one of these is the key intermediate in the reaction here? It basically provides us with the rationale for the anti-Markovnikov addition. Yeah, no, it's not going to be. It's going to be which one? So, right, the first thing that happens, okay, if we go back to the steps, the first thing that happens is the radical is going to break apart. So you end up with, right, you end up with 2 oxygen radicals. Then the oxygen radical reacts with HBr, okay, and then we get an alcohol, plus we end up with a bromine radical, right? So after that, we end up with a bromine radical. I'm leaving part of it out. This is the key, okay? Is that you're making a bromine radical. And so what's the first step, or the key intermediate, is that the bromine radical is going to add to the double bond, right? You get addition on the double bond like this, which would give you this intermediate, okay? This is the key intermediate. So if you have to go back and review the steps of initiation, propagation, and termination for anti-Markovnikov addition across a double bond, then I would highly recommend doing that, okay? I mean, you can definitely cross off this. There's no anion that's formed in this process. We cross that off. There's no cation that's formed here. And B is definitely not a thing, right? Because the first step is the addition of the bromine. If you go back to the rationale as to why does anti-Markovnikov addition occur, right? If I just give you a quick example, if we go over to a blank document here, okay, why do we get anti-Markovnikov addition? Let's see here. Let's say you had this compound here and you treat that with HBr. You're going to get Markovnikov addition. So let me just copy and paste this down here because we'll cover both scenarios, okay? The first step is going to be the addition of the proton so that you end up forming the most stable carbocation, right? And then the bromide is going to add to that. And this is Markovnikov addition. But when you add peroxides, the first thing that happens is the bromine adds first, right? So that you get the most stable radical, okay? and then you do a hydrogen abstraction, and you end up with anti-Markovnikov. So this is anti-Markovnikov. Okay, so if you have to go back and review those steps of the mechanism, I would recommend doing that. All right, let's go back here to some radical chemistry. So we've covered number 1, we've covered number 4. Let's see here. We didn't I didn't ask you to cover number 2, but let's take a look at it. Okay, so here we're doing chlorination of propane, and we're ending up with 2-chloropropane, and then we also end up with some HCl along the way. So it's just, which species represents an intermediate that's formed during the reaction? Could anybody identify it out of these 4 in question number 2? And it's not a trick question. Just look at the answers. We should be able to solve this one by process of elimination. Yeah, exactly, Hannah. This one is going to be the intermediate, right? After the hydrogen abstraction, right? The chlorine radical. So if we draw the hydrogen in here, right? The chlorine radical is going to abstract that hydrogen so that we end up with this radical here. We're definitely not going to form a carbocation. We're not going to form a carbanion, and we don't form a double bond either, okay? So again, go back and review the initiation, propagation, and termination steps of free radical chlorination. Okay, so we covered number 4. Then I wanted to take a look at number 5 because we talked about something along these lines last class. There's a lot of information to squeeze on the slide here, but let me just project the question. It says, what is the expected product of this reaction? So we're taking this compound, so you could call this, if you have methylbenzene, so if we just have a benzene ring and then we have a methyl group on it, we don't call it methylbenzene. Usually we call it toluene, the common name. So you could call this 4-propyl-toluene, this compound here. But when I treat that with bromine and light, okay, we're going to brominate the compound, but where is the bromine going to go? You see in the first answer, A, it ends up on the methyl group. In the second one, it ends up way at the end of this propyl group. Here in C, it ends up at this position here. And in D, well, it's the last one. So the only place it didn't go, they didn't put it, was on the aromatic ring. Could anybody identify where the bromine is going to go preferentially here? So the rationale here, okay, so the rationale is that, again, we have initiation, propagation, and termination. When we're doing a bromination reaction, our initiation is just the formation of the bromine radical. But then propagation is 2 steps. The 2 steps are, first, they're going to be hydrogen abstraction and then halogen abstraction. So in this case, it's going to be bromine abstraction. Okay, those are the 2 propagation steps. So in the propagation steps, that's right, initiation is just making the bromine radical. Okay, so now the bromine radical is going to abstract the hydrogen from somewhere in this molecule. Where are we going to find the weakest carbon-hydrogen bond in this molecule? Let me ask you, does anybody have another guess as to where it's going to be? In C, exactly. Thanks, Jenny, right? It's going to go here because what do we call these positions? Here and here. Could anybody tell me what we call those? Well, maybe you don't want to type it in, but these are called the benzylic position. Okay, the position directly attached to the aromatic ring is a benzylic position. An allylic position is when we have a double bond. Okay, so this is a vinylic, so this would be vinylic, and this position here would be allylic. Okay, so make sure you know vinylic, allylic, and benzylic. And this is these 2 that I have highlighted in yellow and green, these are benzylic positions. If I was to abstract a hydrogen from the green position, I would have a primary, right? So if I was to do this one here, I would end up with a primary benzylic radical. So I'd have this, okay, and then I'd have my propyl group up here. So this is primary benzylic, whereas if I abstracted it to make C, then I'd end up with something that is secondary benzylic. So here's my methyl group, then I have, there's my radical, CH2, CH3. Okay, this one is secondary benzylic. Okay, why are benzylic radicals so stable? Because you can draw a whole load of resonance forms, right? You can draw all the different resonance forms, right? That unpaired electron is delocalized throughout the aromatic ring. So the answer is the bond that's going to be broken is going to be the weakest one. Which bond is the weakest? The one that produces the most stable radical. Where do we get the most stable radical? At the yellow position, which is secondary benzylic. Give me a thumbs up if you're not going to forget that. Anybody? Like, I'm going to remember this now. All right, cool. Good. Let's move on to question number 6. Okay, question number 6. Another radical reaction. It says, which reaction gives an efficient synthesis of 1-bromo 2-methyl propane? Okay, so if you wanted to make this molecule, let's say somebody says, I'm going to give you thousands of dollars if you could just make this molecule for me. And then they give you all these different choices, okay? Now, if I look at the A, and I do, so this is just, this molecule is actually called isobutane. You can call it 2-methyl propane as well. But if I brominate this, okay, where is the bromine going to go? There's two types of protons that could be abstracted. You could abstract the green type or the yellow type. Is it going to go where the green proton is or the yellow type of proton? Could anybody tell me where the bromine is going to go preferentially? Yeah, it's going to go where the green one is. So that is not going to give us the product. That is, in fact, going to give us this compound. That's going to give us tert-butyl bromide. What about the next one? Okay, in number 6, in B, what's going to happen is we're going to protonate. Okay, so if I go to B, we're going to protonate to make OH2 plus, and then that leaving group is going to leave. Okay, so once the leaving group leaves, then it's going to leave, but I'm going to get a proton migrating, or I'm going to get a hydrogen shift at the exact same time, and I'm going to end up with this carbocation, and then the bromide is going to come in, and that's going to give me tert-butyl bromide as well. Okay, what about C? Is C going to give me the correct one? Yes, because this is anti-Markovnikov addition. So that is going to give me 1, 2, 3, 4. That is going to give me the right product, so that had better be the right answer. And the next one is just bromination of the double bond. So if I have 1, 2, 3, that's just going to give me a bromine here and a bromine here. Okay, so that's just dibromination. So there we go. Give me a thumbs up if you follow me on that one. That the anti-Markovnikov addition across that double bond gives you the correct product. Okay, cool. Let's move on to question number 10. So question number 10, okay. Whoop, this one here. It says, at which of the indicated positions would you expect a bromine radical? So if you just had a bromine radical floating around, where is it going to react the fastest? Could anybody answer this? At position 1, 2, 3, or 4? Exactly. It's going to be at position 2. Why? Because this position is what? Starts with B, ends with enzylic. That's right, benzylic. This is the benzylic position. So by far, could you tell me where it's going to react the slowest? Where would it react the slowest? Is it just going to be so sluggish it's never going to happen? Exactly. The slowest is going to be number 1. It's not even going to react, okay? So there you go. So fastest would be at the benzylic position. Slowest is going to be at this vinylic position. Not even going to happen. Not, as George Bush Sr. would say, not going to do it. All right. So number 12, I'm not going to do that one because we didn't cover polymers. Let me go back here. Let's see here. I'm just looking through all of them just to make sure there's no stone unturned. Yeah, we could look at number 3. Remember our textbook? It had some examples that seemed very specific, like the chlorination of methane and then the chlorination of ethane. And I said, yeah, these are very specific examples, but they're used as case studies in any organic chemistry textbook. They all use the same examples. So it wouldn't matter what textbook you used. You can see it showed up in the ACS final, the chlorination of ethane. And it just asks which step would be a propagation step. in the chlorination of ethane. Well, you can see that this one has nothing to do with propagation here. You're just taking a radical and it's abstracting a proton. You end up with the same thing. Here, this would be a termination step, right? You're annihilating. This would also be a termination step. But the last one is where you have the ethane radical abstract. So this one here, this would be halogen abstraction, which is the second step of propagation. So this is propagation. Anyhow, there you go. So that's a little bit of just a touch of free radical chemistry. So who's feeling better about benzylic positions as being, you know, a great place for it to have a radical? Vinylic, not so good, right? It's going to be highly unstable. Okay, cool. Let's turn our attention to something that we didn't cover a ton of, but it is important, and that is redox chemistry. So let me just find the section on oxidation and reduction. I can never remember. Oh, what do you know? I had that in here all along. Okay, so the section on oxidation and reduction. Yes. Okay. You'll see that a lot of the chemistry in this section, it's mostly organic too. It is mostly organic too, but there is some good food for thought for us in here. And I'd say the first one would be question number 4, because we did cover ozonolysis in dirty detail in this class. If you remember ozonolysis of an alkene, right? So that's where we take an alkene. Come on, get a pen. All right. So that's where we take an alkene like this. We treat it with ozone followed by DMS, right? And in this case, you'd end up with a pair of aldehydes, okay? And it depends on the molecule, so you know, times 2. Anyhow, so it says which ozonolysis of which terpene. A terpene is not important what class of compound it is, it's just a type of compound, would give equal molar amounts of these compounds. So you basically have to take each one of these compounds and then just kind of do what we did when we learned this. You know, we'd say, okay, break this here, right? If you do this, you end up with this molecule, then you end up with this molecule, and you end up with, I'm really trying my best to scribble here, then you'd also end up with this molecule. And if you look at the answers, you can actually see that this is the answer, right? You see that this is the acetone, this is this compound, and I'll use purple, okay. Come on. And then, let's see, then this piece here is this piece here. Does everybody see that? Give me a thumbs up if you follow me on the ozonolysis. You just break all the double bonds and then put oxygens at the end of them, right? You can tell that B is wrong right away because kind of the giveaway for B is if you break this bond here, okay, the one at the top, I'm gonna use a thicker pen here, then you would end up with this compound. This is formaldehyde, which is the simplest possible aldehyde, and there's no formaldehyde anywhere in here. So this one can't be correct. Same thing with this one. If you broke this, you would end up with formaldehyde, and there's no formaldehyde in the answer. And then finally, I think what I notice about this one is, first of all, there's no geminal dimethyl anywhere in any of the products. And then I'd also say if you broke this, you'd end up with this compound. This is called acetaldehyde, and that's not in any of them. So there you go. I find that students are usually very good at ozonolysis, you know, figuring out, you know, what the products are and whatnot. So with that in mind, let's take a look at question number 6. So question number 6 says reduction of a triple bond to a transalkene can be accomplished with which set of reagents? Does anybody remember this one? How you reduce an alkyne to a transalkene? So we're taking an alkyne to trans or E alkene. Yeah, thanks, Aaron. Absolutely, Jetty. Perfect. Sodium metal reduction. Right, the way that he writes it in our textbook is he always puts sodium, and I think he always makes sure to put the ammonias in the liquid phase, but that's correct. Right, you see where it says deactivated palladium? That is like the ACS version of Lindlar's catalyst. Okay, so Lindlar's catalyst. Sometimes they call it deactivated palladium. It's totally fine. But that would give you the cis alkene, of course. Let's see. What are some other ones that we covered? Question 13. Yeah, question number 13 is another one that's fair game for us. Yeah, this is a good one here. I like this question quite a bit. So we're starting out with cis-2-butene, this compound here, and then we end up with this diol, right? And you can see that both hydroxyls were added to the same side, right? If you imagine one of them coming up here and then one of them coming up here, they were both added to the same side. So what we're looking for is the formation of a diol, and we want it to proceed via syn addition, meaning both hydroxyls are added to the same face of the molecule. Could anybody identify which one of these conditions would give you that, the syn addition of to make a diol? It's one that we didn't talk about a ton, but it is included in our textbook. It's C, right, Aaron? It's exactly. You know, we were used to using maybe more of the osmium tetroxide in a catalytic amount. In a catalytic amount with NMO, right? That's totally fine. But cold potassium permanganate works well. It's just what the textbook tells you is that it's just a very strong oxidizing agent, but there's nothing wrong with it, especially in a situation like this where there's nothing else to oxidize. So I would say it's totally safe to do this reaction. You know, one that we didn't cover that's not covered in our class is the HiO4, so the periodic acid. If you're wondering what that does, I don't know if it's in our textbook or not, but you know, I don't know exactly everything that's covered on MCAT and DAT, so it might be on there. But if you're wondering what that's for, it's like if you have the diol already. So let's say you had a diol like this, I don't know, something like this, okay? What it's going to do when you treat it with periodic acid is it will end up breaking the diol to give you a pair of carbonyl compounds, okay? But again, we didn't even cover this reaction, but in case you're wondering what the heck is that, that's what it is. Okay, now again, for my students who are very astute, which is all of you, you're going to notice that, like, you see you see the periodic acid is shown here. But again, don't worry about that. You're not going to be tested on that one bit because we didn't cover it. But if you look at a reaction like this one here, right, that's covered in organic too. So don't even worry about that. So this is why I went through them. Same thing with this one here. This is called a Jones oxidation. That's something that's covered in organic too as well. So do not stress about if you see a question and say, we never saw that. Well, there's a good reason. Okay, we didn't cover it. All right. So that covers everything in oxidation reduction. Let's turn our attention to everybody's favorite section, spectroscopy, okay? Because remember, for the ACS final, you get no handout, okay? There is no handout. You cannot bring a handout into the ACS final. But the idea is that by now, it's expected that you have a good idea where a carbonyl is, where a hydroxyl proton is, you know, and the NMR and all that kind of stuff. And you can see that this is the IR table that they give as a reference. But again, you don't have this. They're just saying you should have an idea of these absorbances for different functional groups. Then as far as NMR goes, again, you don't get this, but they expect you to know at least this much, and we've covered that in detail. And then for carbon-13, you can see it's a little more than you had on the Klein, but you know, again, you don't get this, but you're expected to know, you know, a little bit about chemical shifts for carbon as well. So let's go through the ones I had picked. So let's start with question number 1. Okay, question number 1 deals with some ketones. So we have a collection of 1, 2, 3, 4 ketones here, and it's asking us which one is going to give the lowest absorption in the IR. So we have a carbonyl. Carbonyls we know come out around what? I don't know, 1700, somewhere in that vicinity. But we're looking for the one that's going to have the lowest absorption frequency. So I'm going to see if I've done any of these. All right. Yes, you can always bring a periodic table. So if you look in the announcement that I'm going to post, it'll say that you're allowed to bring in a periodic table. You don't need a scientific calculator. You don't need a calculator for that. All right, just a periodic table and some scratch paper and your wits is all you need. Okay, so if we look at this one, um, right, we have carbonyl here, 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 and here, but it's asking us which one is going to have the lowest frequency. Does anybody have any idea about this one? It's based off of something that we went over in class. You could exactly. It's not aromatic, Aaron. So this one is not aromatic, right? So don't. So like this is right. That's just cyclohexene, right? Whereas if you had this, that would be aromatic, right? So those are two different things. But yes, it's based off of resonance because when we looked at wave number, if you remember, wave number was equal to 1 over 2 pi times c times the square root of k over reduced mass, the force constant over the reduced mass. And so basically we can say that wave number is proportional to bond strength. Bond strength. So what does that mean? It means the weaker the bond, the lower the absorption. So we can say here, weaker bond equals lower absorption. And which one of these is the weaker bond? And like Aaron said, it's this one, it's B, because it's the only one that has all of these different resonance structures, right? Every single one of them has this resonance form, right? There's no doubt about that, okay? But B is the only one that has the extra resonance structure because of the conjugation, right? You have double bond, single bond, double bond. So you have 3 resonance forms here. So conjugation, I don't know why this pen doesn't show up over here. Conjugation, okay? There you go, weakens the bond. Give me a thumbs up if you're with me on that. Okay, that's something that we covered again in chapter 14. No? Okay, so chapter 14, okay, if you look at the formula that we went over for wave number, so wave number is this, okay, is this thing here. And wave number, the way you can think about it is wave number is proportional to bond strength, and it's inversely proportional to, so we'll put bond strength, and we can put here wave number is inversely proportional to reduced mass, okay? So there you go. So if you need to review wave number and where it comes from, I suggest doing that. Let's try one, number two. It just says which one of these which compound is consistent with this IR spectrum. So if I zoom in on the infrared spectrum, does anybody recognize any functional groups in here? Any low-hanging fruit, so to speak? Yeah, thanks everybody. Yep, everybody's right on that one. There's definitely an alcohol on here. So I would start there. I'd say, is there an alcohol in the answers? So the first one, this one is a ketone. Then we have an aldehyde. Then we have an alcohol, so I like the looks of that one. And then the last one, we have an ester, right? So the answer has to be C. So that one's a pretty quick one, okay? It's obviously an alcohol. Obvious if you know a little bit about IR. Okay, let's try number 3. Again, you can see some of my scribbles on here, and I apologize for that. But it says, which is the most reasonable structure for a compound with this infrared spectrum? So something that you can do is, and obviously you're not going to bring a ruler into the exam, but you could just make some mental lines here and say, okay, 3,000, right? And then we could make another one around 1,500, is what we recommend, and then try to figure out something after that. But if you look at different absorbances in here, does anybody recognize any kind of absorbance here in this compound? And it's not a trick question or anything. So in this one, in number 3. Yeah. Oh, wow. Yeah. I'd say there's an alkyne in here. Yeah, for sure. Yeah. So we have a stretch here. If you follow this line down here, right, this is 2,000, 2,100. This is at 2,200 centimeters to the -1. So yeah, that would be a triple bond. Yep. Absolutely. There's an alkyne. What else? Oh, yeah, there's a carbonyl for sure. This is a carbonyl stretch in here. And then there's also a carbon oxygen. Aaron, what do you know about Do you guys remember what I said about the carbon-oxygen stretch when it's the strongest signal? Strongest signal. What that usually indicates? Usually, not 100% of the time, but oftentimes. If the CO stretch is the strongest one of all, it's usually, we'll put here, usually an ester. Okay, and obviously there's some kind of carbon oxygen stretch. So if we look at A, it's got a triple bond, it's got an ester. If we look at B, well, we can see it's definitely not an alcohol. If you look at C, it's got a carbonyl, but it has no CO stretch. Okay, and you also see that there's no CH stretch here from an sp hybridized carbon, so we don't have this either. Okay, so, and no sp hybridized CH stretching in here, which would be at around 3,300. So we don't have that. And then in D, there's no aldehydic stretching. We don't see any of that. And then there's no alkene. Okay, there's definitely no alkene in here. And so, yeah, it has to be the first compound, which has the triple bond, which is an internal alkyne, and then the ester. Cool. Awesome. There we go. Let's try number 4. Number 4, which structure is consistent with this infrared spectrum? So if I just zoom in on the spectrum, does anybody recognize any functional groups in here? And again, go with your gut. There are no questions designed to fool you or tease you. Anybody got a hunch about a functional group in this one? Yeah, thanks, Raul. There's a carboxylic acid in here, isn't there? Right, we have the huge OH stretch from a carboxylic acid. So I would start there, and then I'd say, here we have an ester. Here we have a carboxylic acid, so that's in the running. Here we have an aldehyde, so that's not it. And here we have a ketone. So it has to be B. There's no other possibility. And you also see the carbonyl is here, and then I would say that this is probably the CO stretch. Okay, right around there. So there you go. Another one. I'd say that one's nothing's easy in organic chemistry, but I'd say relatively straightforward. You know, my students are usually very, very good at recognizing carboxylic acids. Okay, what did I have next in the list? Sorry, you guys, I got a lot of papers on my desk here. So then we're going to skip ahead to number 11. So number goes to 11. All right, number 11. Here we go. How many signals would you see in the carbon-13 of this compound? Now, I don't know, you know, everybody's unique. We're all unique learners. But what I find is the best thing to do with a question like this is I like to draw a bond line structure. And then I find it easier to assess it. So if I have 1, 2, 3, 4, 5 carbons in the longest chain, so 1, 2, 3, 4, 5 carbons like this, then I have a double bond off here, and then I have a tert-butyl off of here, maybe something like that, okay? So not my prettiest work, but you get the idea. So there's a methyl here, and there's a methyl here. So keep in mind that we have free rotation. We have free rotation around this bond. So if I think about unique types of carbons, all 3 of these methyls are going to be identical, aren't they? Right? Because we have free rotation. And then you see that this, so that's these 3 here. Then we have the quaternary carbon, which is definitely unique. Okay, there's no other carbon like it. Then we have this methylene, which is sp3 hybridized, which is unique because there is another methylene, but that one is sp2 hybridized. So that one is unique. Then we have a carbon that has no hydrogens attached to, I'll use black for that one, that has no hydrogens but is sp2 hybridized. Did I highlight the wrong one? Yeah, I did. Okay, so let me just fix this. The blue. Blue I should have put up here. And then I'd say the last methyl group, that is completely unique as well. There's nothing else like it. So I'll take a purple shade for that one. So we'll put purple and purple. So how many colors do we have? We have a total of 1, 2, 3, 4, 5, 6. So we have a total of 6 signals in this compound. Now, I'm guessing that most of you solved this a lot faster than I did. You just looked at it and said, well, these 3 are chemically equivalent. So there's 1, 2, 3, 4, 5, 6, because those two groups on the end. You know, and if you did it that way, that's totally fine. But I find it handy to draw up online structure sometimes to help me suss that out. Okay, let's try number 12. I think this is a great question, number 12. This is the kind of question you'd see on an MCAT spectroscopy or something like that. Which structure is consistent with this proton NMR spectrum? Okay, we got a whole bunch of different compounds here that are all kind of interesting. This aldehyde, they're all aromatic. So this is aromatic ester. We got an ether here. Here we've got a tertiary amine. We've got an aldehyde aromatic, ketone aromatic. Okay, got all these different functional groups. But let's forget about that for just a sec. We know that whatever we're looking at is aromatic. Let's just look at the proton. And I want to ask you guys, is there anything in here that you guys pick up on right away? I see a few things. Ester and a carboxylic acid. Okay. So, yeah. So, okay. So we have a chemical shift of around 10, right? We have a singlet at 10. So singlet around 10 ppm. So what functional group would that come from? If I have a singlet around 10, because he's just below 10 in this case, but it's right around 10. Does anybody have an idea about that one? Okay, so if we go back, okay, if we look at the table of proton, okay, so whenever we have a singlet that's around 10, so something around 10, that's going to be an aldehyde. Okay, so we've got an aldehyde in the compound. So if we go back here, okay, where was I? So this means this one is referring to an aldehyde. Yeah. Carboxylic acid is higher. It's around 12. So carboxylic acid, right, if you look at the functional group, so this proton is usually around 12 parts per million. Yeah, and aldehyde is only around 10. So that means we've got an aldehyde. So we'll put here aldehyde, and then we can go back to the answers, and we can get rid of this one, and we can get rid of this one because they don't have an aldehyde in them, okay? Now, what else do we see here? Notice that we have a quartet and a triplet. This is a quartet and a triplet, and it looks like the spacing or the coupling constants are the same. Does anybody remember what kind of alkyl group is represented by a quartet with a higher chemical shift and then a triplet with a lower chemical shift? It's one of the big three. That's right, Aaron. It's an ethyl group. So that means that we've got an ethyl group, CH2, CH3. We might have one, we might have two, I don't know, but we have an ethyl group somewhere. And if you look at A, it's got two ethyl groups. And if you look at B, or C, rather, it's got two ethyl groups. So still, we don't have anything that takes us all the way to determine whether it's A or C. So where we're going to decide is actually by looking in the aromatic region. Now remember, aromatic is somewhere around 6.5 to 8. So this is aromatic. Do you guys remember what I told you when you have two doublets that are leaning in towards each other like this? Does anybody remember what that represents on an aromatic ring? Something that I went over with you in the second day of lecture on NMR this summer. Okay, so when we have two doublets leaning in towards each other like that, what it means is that your aromatic ring has two different substituents and they're in the 1,4 position, right? So 1, 2, 3, 4. So we say it's 1,4 di substitution, okay? Another way to put it, you could say it's also called para substitution. Either one is totally fine. And so that tells us that it has to be C, okay? Because this one has got 1,4 substitution, whereas this one is mono substituted, okay? So again, if you have in the aromatic section, if you have two doublets and you see how these two are kind of pointing in towards each other, right? They're kind of leaning in like that, okay? That means you've got a pair of doublets and you've got 1,4 or para di substitution on an aromatic ring, okay? So that's how you would clear that one up. What was the next one? Was 13. Question number 13. Oh, I like this one too. It just says, which structure is consistent with this NMR spectrum? In number 13. So starting on the far right, we have a doublet. It looks like a doublet to me. So if you zoom in here, you can see this is, you can see it's 2 peaks, right? You got one here and one here. So this is a doublet that integrates for 6 protons. Here we count, we have a total of, what would this be? It looks like 1, 2, 3, 4, 5, 6, 7, 8, 9 is what it looks like to me. So this is a non-net. It's a lot of peaks there, okay? But that integrates for 1 proton. And then we have a doublet. So this again looks like a doublet to me, a doublet that integrates for 2 protons. And then we have a singlet that integrates for 1 proton. That's around 4. So you can see that all 4 of these compounds are alcohols. Are you talking about this one, Isaac? Yes, it comes from this proton. It's the aldehyde proton. Does that help? Aldehyde proton is always a singlet around 10. The spike at 0, could anybody tell us what the spike at 0 is? If you look, there's one at 0 there. There's one at 0 here. There we go. They all should have something at 0. Right? At 0, it's tetramethylsilane, TMS. Right? So this is the reference, TMS, tetramethylsilane, which is set at 0. Okay? All right. Does that help? It's the reference. It's what we base the chemical shifts off of, is TMS. Okay, so if we look at this compound here, you know, it's actually kind of fun to do with a problem like this. It's just kind of study each compound and kind of figure out what kind of spectrum you would get. If you look at A is just this. It's tert-butyl alcohol. So for that, you would get you'd get a singlet that integrates for 9 protons. So this is definitely not the answer. If you start looking at the multiplicity in B, this would give you a triplet. This would give you a sextet because it's coupled to 5. This one would give you a pentet, which we don't have. This one would give you a triplet. And this one would give you a singlet. Okay, so this is obviously not it because we don't have any triplets. We don't have any pentets in our compound. If we go over to D, so if we do D, this one would give you a doublet. This one would give you a sextet. This would give you a singlet. And then this one here is coupled to 4 protons. So that would give you a pentet, which we don't have, pentet. And then this one here would give you a triplet. So again, there's no triplets. If we look at C, though, so if I just draw the bond line structure of C, which looks like this, okay? So this proton, the alcohol is never split. This is going to give you a singlet, so that makes sense, okay? Now, these 2 protons here, right, these are split by this proton here, so that's going to give me a doublet that integrates for 2 protons. Now, if I look at the 2 methyl groups here, right, those are chemically equivalent because there's free rotation around this bond. They're only coupled to this 1 proton here, so that's going to give me a doublet that integrates for 6 protons. And then lastly, if I look at this guy here, he's coupled next to 1, 2, 3, 4, 5, 6, 7, 8. So n plus 1, neighbors plus 1, gives me a nonette that has an integration of with an integration of 1 proton. Okay, so this has to be the right compound here. Okay, so if you have to go back and review the old n plus 1 rule, make sure you do that and that you understand splitting. Okay, give me a thumbs up if you follow me on that one. I think that one's a really good question, this one here. Okay, cool. Let's try number 17. Number 17, which is this one here. So the reason I wanted to show you this one, I'll just tell you right now, there is none of this on your exam. Okay, there's none of this where it says T and Q, but I have a couple of students who have expressed interest in writing the MCAT and the DAD, there's no PCAD anymore, okay, but maybe an exam that involves organic chemistry, and they still use these sometimes. So if you remember when we looked at carbon 13, okay, so this is a carbon 13 spectrum right here. You guys recognize that. It goes from 0 to 220 ppm. Now, every spectrum that we looked at was called a decoupled spectrum, where there's no coupling between the carbons and the protons that are attached to them. And you can see that every signal here is a singlet too, okay? So this is the singlet, 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 et cetera, et cetera. But if you're wondering what the little Q and the T stand for, the Q stands for quartet, so quartet, and the T stands for triplet, okay, and the S stands for singlet. And this is actually the N+1 rule applied to a carbon 13. But what it means is if you have a quartet, that means that there's 3 protons attached to the carbon. If you have a triplet, it means there's 2. If there's a singlet, it means there's 0. So in other words, I'll summarize it here. If it says Q above it, it means it's a methyl. If it says T above it, that means it's a methylene. If it says doublet, that would mean it's a methyne. We don't have any of those. And then if it's a singlet, that means it's a carbon that has no hydrogens attached to it. So that tells us that we have methyl, methylene, methyl, methylene, and then this one here has no hydrogens attached to it, but it's all the way up at 200. So that tells us that it's a carbonyl of some sort, okay? Now again, if you're wondering where do the T's and Q's come from, it's just a different type of experiment that is run. It's like a version of ADEPT, okay? It's like a different version of ADEPT experiment. But there you go. So that's what that means. So now if we go and we look at the answers, you can see that all 4 of them have, I think they do, yeah, all 4 of them have 2 methyl groups and then 2 methylenes. So they all have that, and then they all have a carbonyl. So they all have, even this one has 2 methyls, right? Because these 2 are chemically equivalent, 2 methylenes. Oh, actually, the last one doesn't have a carbonyl, does it? It has an alcohol. So we can cross this one off. Okay, so now we have the other ones, and now we're going to have to go to the proton. Okay, so we have a triplet that integrates for 3. We have, it's hard to tell with this one here, but it looks like we've got 1, 2, 3, 4, 5, 6. This looks like a sextet to me that integrates for 2 protons. Here we have a singlet that integrates for 3, and then we have a triplet that integrates for 2. So we're looking for 2 triplets, a sextet, and a singlet, I guess. If you look at A, we have a singlet for this one. We have a triplet for this one. We would have a sextet for this one, and we would have a triplet for this one. So that's in the running. Then if we go to B, oh, these are good. We have a singlet here, we have a triplet here, we have a sextet here, and we have a triplet here. Oh, sugar, okay? And then if you look at the last one, look at this, you guys. We have a singlet, we have a triplet, we have a sextet, and we have a triplet. Who comes up with these kinds of things, okay? So all 3 of these, A, B, and C, would give the same multiplicities. So how are we going to solve it? Using what technique? Does anybody know? Starts with C, ends with chemical shift. That's right, chemical shift. So we're going to have to figure out the chemical shift of everything. There's a couple of ways you could do it. I think that probably the easiest way to do this is to use the ester. Right? Do you guys remember an ester? So if you have a methyl next to the oxygen of an ester, you take the baseline, which is 0.9 ppm, and then you would add 3 to that. So you'd get 3.9 ppm for your singlet. Well, you can see the singlet comes out at what? 2.1 ppm. So I could cross this one off. Then if you look at the singlet in B, you'd say the baseline is 0.9, but it's next to a carbonyl of a, so then you just add 1. So that would give you 1.9 ppm. So that's a contender because that's very close to 2.1. Then if you look at C, oh man, it's the same thing again. You end up with 0.9 ppm plus 1 because it's next to a carbonyl. So that equals 1.9 ppm. So both of those. So now B and C are still in the running. So we've crossed off A. So then what we'll do is we'll look for, why don't we look for the triplet that integrates for 2 protons, right? So there's a triplet that integrates for 2 protons. If I highlight it, This guy can be either this or this. So what was the baseline for a methylene? Okay, so I'm going to scribble these down in blue, okay? So the baseline for a methylene was 1.2. So we have 1.2 ppm. And then it's next to a carbonyl. So we're going to add 1. That would give us 2.2 ppm, okay? This one is at 2.123. It's around 2.4 ppm. Then if we look at this one here, we'd say 1.2 ppm. And then you would add 3 because it's next to the oxygen of an ester, which would give us 4.2 ppm, which is way too high. 4.2 is like up here somewhere. And so that would mean that B has to be the answer. So you really have to dig your heels in to figure this one out. You can cross D off right away because it's an alcohol. And then you can cross A off because of the methyl, which has too low of a chemical shift. But then you have to kind of go through quite a few of the chemical shifts for B and C to figure out that it is actually, in fact, B. Okay. Give me a thumbs up if you're at least with me on the rationale. Everybody with me on the rationale for that one? Cool. Yeah. Awesome. And I think that's it for spectroscopy. Those are the ones that I had picked out. Let's see here. This is a good one. Number 15. I bet you guys could solve this faster than me. Number 15. The chemical shifts in the carbon-13 spectrum for this compound are 15.8, 40.1, 51.8, and 170.2 parts per million. Which is the correct set of chemical shifts? So we've got carbon number 1, 2, 3, and 4. Well, which number has to be carbon number 2? Who could answer that? Carbon number 2 has to be which one? It's a carbonyl. There's no debate. Exactly. Thanks, Rule. So that means it's got to be either C or D. We can cross these off because the carbonyl cannot have that kind of chemical shift. So then I would go to the lowest one. Which one of these other three, is it 1, 3, or 4 that has the lowest chemical shift? Go with your gut. Which one has the lowest chemical shift? Bottom of the barrel, right, Jenny? Absolutely. It's number 4. So then I would look at number 4 and I would say it's got to be this one, right? Because it's got the lowest one. So there I go. D, done. Done. D for done. Okay. See, again, questions you guys can answer very quickly with, you don't need my help. Okay, let's go to synthesis for a minute or two. Now, again, most of the synthesis that you're going to see in here, it's mostly chemistry 3111, which you guys will all take and crush these, okay, when you're done. But again, a lot of this chemistry hasn't been covered. But a question like 3 would be totally reasonable because all the content in this one was covered in chapter 9 in the alkynes chapter. So we're taking propyne, so propyne, this compound here, and then we're treating it with sodium amide. So number 1 is going to be what? After you deprotonate, you're going to have this alkanide. Excuse me. Then you treat it with methyl bromide. You guys can all draw the mechanism for the S. Well, that's a pretty funny looking arrow. Anyhow, you guys can all, that's not much better. You guys can all draw the curved arrows for that. Again, faster than I can. So you end up with 2-butyne, which is going to be compound number 2. Then you treat that with water, sulfuric acid, and mercury 2 sulfate. So that normally this is a Markov-Nikov addition of water, but this is just hydration. Since this alkyne is symmetrical, it doesn't matter where you add it, right? You're going to end up with an enol, which is going to look like this, but you know that the enol is going to tautomerize to give you what? It's going to tautomerize to give you a ketone, so it's going to give you this ketone right here. So this is going to be the final product, okay? Who remembers doing this? Anybody thumbs up on remember? Okay, good. All right, awesome. Let's see. Like, for example, you guys look at this and you're like, what is this? Magnesium? What the heck is that used for? That is something that we haven't covered even for 1 second in this class. This is covered in chapter 12 of organic chemistry too, so a lot of you will probably learn this in September. Same thing, you see that magnesium. So let's scooch all the way up to question number 24, which is appropriate for us as chemistry 3101 students. Yeah, this again is like a type of MCAT or DAT question where they love to put a little, they love to write a like a blurb ahead of time. You know, they love blurb questions. Anyhow, it says an optically active alcohol with a molecular formula of C5H8O undergoes hydrogenation over platinum to give an optically inactive alcohol. Which of these alcohols is consistent with this data? Okay, so there's a lot to unpack here, but and this is not a trick. Okay, does anybody remember what it means when it says it's optically active? Could give me a one-word answer. What does optically active mean? Exactly, Jenny. It means it's chiral. Exactly. So we have a chiral compound. Okay. So now we know that one of these alcohols we're looking for a chiral compound. So Jenny, I don't want to bug you. Okay. But Jenny, would that be a chiral compound, or anybody? Is that a chiral compound? And I'm not trying to fool you. It's not a chiral compound, right? There's no chiral center in there. So right away you can start eliminating this. What about D? Is that a chiral compound? That look chiral to absolutely not. Right? Scratch that off too. Right? So again, we're kind of just using some process of elimination. I don't know about you, but I can't help myself. I like to just start kind of looking through the answers right away. But then another thing you could do is, and this won't really help you a ton with the way they laid this question out, but you could take the formula and you could calculate the HDI. The HDI for this compound, whatever it is 2, but you see that every damn thing they gave you, pardon my language, everything here has an HDI of 2. So that actually doesn't help all that much. But anyhow, so then it says if you do a hydrogenation over platinum, so that means it's going to reduce it completely, you end up with something that is achiral. Well, I didn't go over this with you, but I'm pretty sure you guys could figure out that this carbon is chiral and this carbon is chiral. So both of those carbons are chiral, right? They both are some kind of stereocenter. So if I was to do a reduction on this one, okay, hydrogen and platinum, or a reduction on this one, go backwards, hydrogen and platinum. For this one, you notice you have 1, 2, 3, 4, 5. So you'd have 1, 2, 3, 4, 5. And then you have the hydroxyl. So you go from something with a chiral center to something that has no chiral centers. Okay, so that should hopefully be the answer. Because when you reduce the other one, again, you have 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5. But now when you reduce, you still have a chiral center. That's still chiral. So the answer has to be A for that one. All right, Hannah, let me go back. So it's question number 3. Yeah, so you end up with a ketone. Yeah, you end up with a ketone. It's a methyl ketone. Okay, yeah, so it's this compound here. The compound name, which you don't have to know how to name a ketone, but this is called butanone. Butanone. You can probably guess where that name comes from. 4 carbons. That's a ketone. Okay, so butanone. Okay. Yeah, no problem at all. Let's go back to 24 just for a sec here. Does this one make sense to everybody? Give me a thought. Or is there any questions about this one? Right? This is again, this is like a classic type of MCAT or DAT question where they love to ask a few little tidbits all in the same question. They love to squeeze as much in there as they can, but it's usually concepts that you guys know really well. Okay, 25. I like this kind of question. There aren't a ton of these on your final, but I like questions like this because it tests my students on their synthesis. So this one, I actually, it's question 25. Da, 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 I thought I'd written them all down. Darn it. Anyhow. 1, 2. Okay. I don't have enough room to scribble all of these on here, but again, I feel like these are just, this is an excellent question. So I'm going to actually find it in my manual here so we can go through all of these together and then figure out which one is going to give us, because I want to solve this on a blank page with you. Which question is it? Number 25. Okay, so let me go over to a blank document Just give me a sec here. Okay, so this is question 25. So question 25. So what it says is you want to go from here. So you want to take 2-butyne, and then you want to make this diol, okay, where they have one hydroxyl up here, one hydroxyl up here. And then they're very clear that you have this methyl and this methyl coming out, okay, like this. And then you have the proton in the back and the proton in the back, like that, okay? So, yeah, okay, something like that. So let's see here. So in the first one, it says if you took this compound and then you treated it with H2 and deactivated palladium, okay? So H2 and deactivated. Remember, I told you that deactivated palladium is the same thing as Lindlar's catalyst. So that would give you the cis alkene. So I'm going to mix bond line structures in here just for interest's sake. Now the next one, it says osmium tetraoxide and H2O2. So when you do that, that's the same thing. So osmium tetroxide, and it says here catalytic amount, okay, and then H2O2. H2O2 is another form of a co-oxidant, so it's like NMO. And in that case, that gives you a syn addition. So you would actually end up with the product, right? Because both alcohols are going to end up on the same side and both methyls are going to end up on the same side. Why? Because again, this is syn addition, okay? So you get a cis alkene. So that means that the two methyl groups are still going to be cis to each other. Now, if we go to number 2, so in number 2, we're taking the same starting material. Again, I'll use a bond line structure here. Now we're going to use sodium metal reduction, which you guys know gives you the transalkene, okay? And then we're going to treat it with osmium tetroxide in a catalytic amount. Well, this already stinks. It doesn't look like we're going to get the same thing, right? Because now we're going to get anti-addition, okay? So anti-addition. And so now our two methyl groups are going to be opposite of each other when we get our we're going to have our two hydroxyls being anti to each other, but we're also going to have our methyl groups being anti to each other. So in this case, so we'd end up with one. No, sorry, did I say anti? I meant syn. Okay, so we're syn and shit. Pardon my language. I should not post this to YouTube. Anyhow, so I get syn addition of the alcohols. Sorry, Mr. Dion needs another coffee, I think. But now you're going to have your two methyl groups being trans to each other, okay? So this is not going to work. So we can scratch number 2 off of there. Okay, so now we go to number 3. Hopefully I'll think more clearly this time. So we're taking the 2-butyne. We treat it with H2 and deactivated platinum or palladium, whatever it says, and that is going to give us the cis alkene. Then after that, we're going to treat it with a peroxy acid. So that is going to give us an epoxide. But remember, both of your methyl groups are going to end up on the same side when we do the epoxidation. So then we're going to crack it open. It says H2O and sodium hydroxide. This is not something that we covered in detail, but it's just another way to crack this open. So it's exactly what you think would happen, is that the hydroxide acts as a nucleophile and it cracks that open like this. So in that case, we're going to end up with, again, we're going to end up with an anti-addition. So we'll put here anti-addition like that. So one hydroxyl is going to be like this. The other hydroxyl is going to be like this. So that means that one methyl group is going to be coming out and one's going to be going in. So this doesn't work as well. Then if we look at number 4, okay, we have the 2-butyne again, like this. And now we're going to treat it with sodium metal reduction. And that gives us the transalkene, like that. And then we're going to treat it with a peroxy acid again. So we're going to treat RCO3H and then H2O and sodium hydroxide, which again just opens up the ring. But remember, that's son of a gun. anti-addition, like that. So now we're going to have our anti-addition of our hydroxyls, okay? So we're going to end up with, so I'll do it differently this time. So we're going to end up with one up here, and we're going to have one down here, like this, but we're going to have one methyl group coming out of the page like this, and the other one going back like that, okay? So what kind of compound is this? Well, if we rotate it, then we see that, oops, if you put both hydroxyls in the same plane, you actually end up with the right compound. So you actually end up with both methyl groups being on the same side like this. So this is going to work. So the answer is going to be number 1 and number 4. So 1 and 4 for this one. This is a pretty tough problem. So the answer is 1 and 4. Yeah, which is D. Okay, I'm going to